Alex Hall is an associate professor in the UCLA Department of Atmospheric and Oceanic Sciences. He is, folks, one of the world leaders on climate change. He's a member of the IPCC, the Intergovernmental Panel on Climate Change. Indeed, he is one of the lead authors of the forthcoming IPCC report on climate change. He is one of the leaders of CLIVAR, a national climate initiative. He is a reviewer and a board member for a number of important panels which look at the climatic research of our nation. He has been recognized by many, many awards, including an NSF Young Researchers Award, which is extremely, extremely difficult to get. Alex's purview in terms of his research is amazing. He's worked on some of the most important questions of our time: Arctic sea ice retreat, the impacts of climate change on things like snow in the Sierra Nevada, or indeed the city of Los Angeles. It really is just an incredible, incredible record for such a gifted and young scientist. Alex has then developed, though, over the last few years in particular, a profound interest, a dedication to making his research relevant, to making his research help the community, the city, and the state in which he lives. And so he has worked closely with the Institute of Environment and Sustainability and with the LARC. He has become the director of the Institute's Center for Climate Change Solutions. He's working on the highest level of climate research, but he's bringing it down to the level in which policymakers and the general public can use, that it can actually help us with adaptation. And he is dedicated to this. And to see a superb physical scientist like this moving and also working so well in the world of policy and applied aspects is really, really quite amazing. And his work with LARC is an example of that. Now, last year, about this time of year, with Mayor Villaraigosa, he released a peer-reviewed report on the impacts of climate change on our city in the year 2050. Not that far in the future, folks, not that far in the future. This was not like any of the climate reports you've ever seen before. This was internationally groundbreaking. Instead of talking about generalities of what was going to happen at the level of the state or the continent, he was able to use mathematical downscaling and physical techniques to actually take climate change projections and bring them down to the neighborhood level. He brought them down to the level of a spatial resolution of 1.2 miles. How far is that? That's your neighborhood. That's how far you can walk in about 20 to 30 minutes. That's the walk from your place to Starbucks or to Vaughn's or Gelson's. That's the level of analysis he's done, and he found some pretty startling things. If you remember the reports on this in the LA Times and things like that, Mayor Villaraigosa's conference, he found that in general, by 2050, this area could heat by about 4.7 degrees Fahrenheit. But it's not going to be equally distributed. Areas near the coast will be hotter. Areas inland will be cooler, rather. Areas inland will really suffer the brunt of this. This is taking what's coming down the road to us and putting it in a form that can inform policy, that it can inform us, the people that live in these neighborhoods, the neighborhoods in which our children will live. Ladies and gentlemen, Alex is going to share his work with us tonight. He's worked hard on this. This is a real treat for us. Let's give him a huge round of applause and thank him for what he's done.
Well, it's really a pleasure to be here, and I want to thank Glenn. On a personal note, it's really been wonderful to see the Institute of the Environment and Sustainability grow so much over the past few years under your leadership, and that's one of the things that's so attractive about being at UCLA is the Institute of the Environment and Sustainability. So thank you, Glenn, for everything you've done. And I have to say, it seems like yesterday that I was just a graduate student, and I hardly recognized myself in that description that you just gave of me. But I did do something really exciting over the past couple of years with my research group, and I'm here today to talk to you about it. And as Glenn said, that the topic of the day is the impact of climate change on the Los Angeles region. And I have a number of results to share with you. Some of them have already been released. The ones that Glenn alluded to are some of those. I'm also going to give you some hints of some things to come, some studies that we'll be releasing over the next few months. And I'll also be outlining some of the future work that we still need to do in this area. So this is hopefully a very satisfying view of what we've done and what we are doing, and a sense of what is still to be done. All right, so I have planned a 6-course meal for you tonight. First, I want to give you some background about climate modeling, because those are the tools that we use as scientists to understand the climate. So that's your salad. And then next, I'm going to give you some information about the methods that we use to do our research. I'm going to call that your pasta course, okay? And then next, we're going to get into the meat of the talk, which is the climate change projections that we did for Los Angeles. Okay, that's your meat. Then I'm actually going to transform from a scientist into an actual human being. And I'm going to give some personal thoughts on what I think these results mean for Los Angeles. And then, so that's going to be your cheese course, okay? Then I'm going to ask the question whether we just need to adapt to climate change or whether we ought to do more than that. And it'll be clear later why that question is so important. So that's going to be your actual dessert. And then for petit fours, we'll talk about the road ahead, okay? So an intellectual feast awaits you. All right. So first, a little bit of an amuse-bouche. Okay, we're not quite into the salad yet. I first want to mention what I'm not talking about tonight, okay? I'm not going to be talking about the problem of global climate change and whether it's happening, whether there's a human role in global climate change. I'm going to assume that you all are card-carrying members of the reality-based community. And that, right? And that you understand the basic issues, okay? Climate change is occurring as evidenced by this increase in global mean temperature over the past century. And humans, as most scientists have concluded after exhaustive research over generations, that humans have some role in this. All right. What I am going to talk about is something that I think is very important for us. What does this change mean for us? There really isn't an organism or a person on the planet that cares what the global mean temperature is. That's just a statistical abstraction. The important thing is, how does this change in our environment, this global transformation, manifest itself in the areas that we actually live? And this is a particularly important question for Los Angeles because, as we all know, having probably been in many different parts of our region, there's a lot of variation in climate across the landscape. And this variation arises from the fact that we have a complex coastline and we have a series of mountain complexes that generate microclimates in Los Angeles. For example, the San Fernando Valley, on average, is a lot warmer than the Los Angeles Basin. And that's just a fact about our present-day climate that we know to be true. And it's easy to imagine that in the future, due to global climate change, the San Fernando Valley might respond differently to this increase in temperature and this change in climate. So what does this global mean change in temperature mean for us? That's what I want to talk about. Another important point to make about Los Angeles, another thing that's special about the climate in this region is that the reason why this city exists is because of our climate. Los Angeles is a world-class city because we have such a great climate. I'm sure you've all had conversations with people from New York and other cities, this argument, New York versus LA, which is the best city, and they trot out all the wonderful culture there is in New York and the street life and all those things. And then we always have this little trump card in our pockets, right, that we can pull out. But you have crappy weather. We always can say that about our region. So the climate is really important for Los Angeles, and it's a precious resource that is very valuable to us. And that's a little bit different from other places. All right, a few words about some of the important factors that affect climate in this region. So here's just a map of the region. You can see the Channel Islands here on the left and the Mojave Desert in the upper right. Okay. Usually it's pretty nice here. Occasionally we do get rain, okay? And that occurs when flow comes from the ocean towards the interior. And as those moist flows from the ocean flow over the mountain landscapes, they dump a lot of rainfall and occasionally also snowfall onto these areas of high elevation. That's one aspect of our climate that's important. And secondly, we also have something called the Santa Anas. These shape our climate, especially in the early fall. They arise because as the desert begins to cool off, as the sun wanes in the seasonal cycle, the desert cools off, and the air in the desert becomes very, very cold and dense. And that dense air wants to flow down towards the coastline. And that drainage those drainage events are essentially Santa Ana events. So that's also a key element of our climate, and of course, a key element in the fire ecology of our region, as we all know. So those are the basics about the climate where we live. And just to state, I think the obvious, climate change is coming to us, and the question here is, what are these effects going to be? For example, if we have a global change in temperature, we might expect local changes in temperature as well. So how much warmer is it going to be here, and where will that warmth be distributed? We also have questions about wildfire. Our fires in this region are climate-driven. They're climate and weather-driven. And we have to understand the implications of a changing climate for changes in wildfire ecology. And finally, we are in a semi-arid region. We don't have a lot of water resources locally, and that means that we're quite vulnerable to changes in water resources. So these are I think, the key questions that we have to confront in looking at this issue of climate change. All right, so onwards now to your salad. A few words about climate models. What I want to do in the next 3 minutes is demystify the phrase climate model. I'm sure many of you have heard this phrase in the newspaper many times, and I want to just give you a basic working definition of what a climate model is, because we're going to be using these tools to understand climate change. So all of science involves theory and observations. Those are the two pillars of science. And the theory of science is essentially expressed always in mathematical form. We have equations that we think describe how the real world works. Here is an example of an equation, and you don't have to take notes on this. Don't worry, I'm not going to test you on this or anything like that. This is an example of an equation that is used to describe the motion of air on the Earth's surface. This is an equation that is included in a climate model. And indeed, a climate model is essentially a compendium of the equations that describe the inner workings of the climate system, the motion of air and water on the Earth, the interaction between the atmosphere and the ocean, exchange of heat and water between the atmosphere and the ocean. These can all be kept track of in mathematical terms. Now, these equations, it turns out, are incredibly complicated, and they cannot be solved with traditional methods like the pencil and paper methods that you use in your high school algebra classes. These equations must be solved with computing technology. And essentially what we do is we instruct a computer to solve all these equations and make them communicate with one another to capture the full complexity of the climate system. And this is a little bit of snippet of computing code of one of the global climate models. This happens to be the one developed at the Goddard Institute for Space Studies in New York City. This is just a tiny little piece of a giant amount of computing code, thousands and thousands of lines. And these climate models are incredibly complex pieces of engineering, and I would compare them in complexity to some of the great works of civil engineering that many of you are familiar with. For example, the Hoover Dam, a great work of civil engineering, very complex to put together. That's the scale of a climate model. So it's really kind of an amazing thing when you think about it, that we as a species have the ability to grasp the essence of the inner workings of our planet and incorporate that understanding into a computer and simulate with a computer our climate. That is an amazing thing, and a good thing that we can do that, because it so happens that we need that tool to understand what we're doing to the environment. All right, so a climate model, once it gets all these equations and its instructions and it solves them, it produces output. It spits out information. This is an example of the kind of information that you get from a climate model. This is just, in this case, temperature at the Earth's surface. This happens to be looking over the Eurasian continent. And you can see that this information is provided on a grid. And we can also impose now information on the model and have it respond. So we can, for example, change the concentrations of greenhouse gases in these models. And we can see how the climate changes, how the climate responds to these changes in greenhouse gases. So it's very useful, obviously, to be able to simulate the climate's response to a change in greenhouse gases. So let's just look at a scenario of greenhouse gas changes. This is, on the x-axis here, are years. So going from the late 19th century all the way to the end of the 21st century. On the y-axis, we have the concentrations of carbon dioxide in parts per million. Carbon dioxide being, of course, the main greenhouse gas that is increasing due to human activity. All right, so here's the observed change in carbon dioxide over mainly the 20th century. You can see a nice, healthy increase. And I've highlighted in red this number 400 on the left side. I don't know if you guys saw the headlines the other day, but we just passed 400 parts per million of CO2 concentrations. This is a very timely plot here. Okay, so this is the historical change in CO2. We also can imagine a scenario of future changes in CO2. And we might imagine, if we wanted to impose a logical scenario on a climate model, that we would just imagine that the CO2 changes would continue the same way they have been changing. In other words, we would continue to increase our emissions of carbon into the atmosphere, and carbon dioxide concentrations would continue to increase. And that is the scenario that I'm outlining here in red. This is what I'm going to call the business as usual scenario, where we keep on increasing greenhouse gases at the same rate that we have been. Okay, now, we can take this emission scenario and we can impose it on a climate model and see how a climate model responds. And it turns out that there are roughly 30 climate models that have been developed around the world at various modeling centers. And each one of these climate models can experience this same emission scenario. And in fact, one of the wonderful things the IPCC has done, which Glenn mentioned, is to coordinate these emission scenarios so that every modeling group around the world can use the same emission scenario and see how their model responds to these increases in greenhouse gas concentrations. So this is a little bit of a pile of spaghetti here. This is the change in temperature, in global temperature, when you impose this this historical change in greenhouse gases plus the business as usual emission scenario. Okay, so we have the black here is showing the response of the CO2 historical change, and then the red is showing the model's response to this business as usual emission scenario over the course of the 21st century. And you can see, of course, rising temperatures in these models as a response to these changes in greenhouse gases. Another thing that you'll notice is that the models don't respond in all the same way. Each one of those curves represents the response of a different model. So there's a model that gives you the least amount of warming by the year 2100. There's a model that gives you the most warming by the year 2100. And there's also a range of response. And that range arises from the fact that it's possible for an intelligent, smart group of scientists to construct a different kind of model from another group of intelligent, smart scientists. So there's a range of outcomes because there's no unique way to construct a climate model. So we have what we call an uncertainty range associated with this warming that's due to the fact that there are different ways, plausible ways to build a climate model. And this is one of the caveats about climate models is they don't give a single answer, really. If you take the collection of global models that have been developed around the world, they give a range of responses. And it's the common practice in the climate science community is to take the average of the models to produce the most likely outcome. And we call that, it's kind of a technical term, we call that the ensemble mean. The ensemble is the group of models. The average of the models is the ensemble mean. So the most likely warming by 2100 corresponds to that blue arrow on the right-hand side of this picture. So this is one of the caveats about global climate models that give different answers. And this is important for us in our study because we want to encapsulate this uncertainty at the regional scale as well. We don't want to lose that information. Okay, another problem with these global models, I think you saw this already in the picture I showed you of the output earlier. These models have a pretty coarse resolution. And this is just an example, and again, another example of an output from a climate simulation. This is, again, temperature at the surface. And you can see that the grid boxes of this model are much larger than the areas that we are actually interested in. And just to put this into more perspective, here's a map of the Southern California region with some place names down there on the bottom. And here is the grid of the highest resolution global climate model that is currently available. And you can see that the variation across the landscape in topography is very significant compared to the resolution of the model. So for example, if you look over here at this grid box, you can see that within this single grid box, we have part of the San Gabriel Valley, San Gabriel Mountains, and the Antelope Valley, all within the same grid box. And the global model would represent that with one single number. So there'd be one single warming value, for example, for that grid box. And that's not good enough for us. Obviously, there's a lot of variation within that landscape that we have to capture. So this is one of the issues that we have to face. So the scientific challenge for us was, how do we bring these global models down to scale? How do we zoom in on the Los Angeles region, number one? And number two, how do we account for the fact that there really are different outcomes among these global models? There's not one single answer. There's a most likely outcome, and there's an uncertainty associated with it. All right, so that was the salad. This is now the pasta. I'm going to talk to you a little bit about some of the methods that we used. Okay, so, and I want to also acknowledge at this point Sea Change LA, which is the website that was developed by Climate Resolve, this organization that Jonathan Parfrey heads up. They're the ones who provided a lot of the communications for this project, and you can go to that website and find more information about it if you'd like to. So these are, this is also just a little palette cleanser. Also, these are the people who do this work. Obviously, this is done by people, and it's a wonderful group of people, and I want to acknowledge them. Neil Berg, Florent Briand, Scott Capps, Jerry Wang, Alex Juice, Mark Nakamura, Shin Ku, Catherine Reich, Marla Schwartz, Feng Peng Sun, and Daniel Walton, all wonderful people and have done really wonderful work in association with this project. So yes, let's give them a round of applause. All right, so as I mentioned, these models, these global models have very coarse grids. So what we have done is taken these global models and we have imposed them on what we call a regional climate model. A regional climate model is the same thing as a global model, except that we run the model at very high resolution and we run it over a limited area so that we can take all of those precious computing resources and invest them in very high resolution. And the global models, I should mention, require enormous computing resources. They're all done on supercomputers. And likewise, the regional simulations that we have done were done on supercomputers here at UCLA. And they involved an astronomical number of calculations, and they took months and months to complete. So there's very heavy data involved in both the global modeling and the regional modeling. So it's a very complex operation involving really the entire global climate community's efforts and our efforts here. And it took us about 2 years to do the simulations and the research that I'm going to show you. So this is a big effort. All right, so I mentioned the resolution issue. We needed to zoom in on the Los Angeles region, and I want to show you how high our resolution is so that you can get a sense, compared to the global models, the resolution of this regional climate model that I told you about. So here is a part of the Los Angeles region with some neighborhoods and cities identified. And here is this 1.2 mile or 2 kilometer grid that Glenn referred to in his introductory remarks. And you can see that at this resolution, we really are getting down to what we call the neighborhood scale. And more importantly for this science, we are resolving these mountain complexes that are so important for shaping regional climate. We are resolving the Santa Monica Mountains, for example, and this important difference between the San Fernando Valley and the Los Angeles Basin. So the name of the game, basically, is to take these global climate models and impose them on these regional simulations and then determine what regional conditions at this high resolution are consistent with the global models. So we get a variety of regional outcomes because the global models all give different answers as well. And that allows us to give spatially explicit information about most likely outcomes and also the uncertainty. Okay, we looked at 2 different emission scenarios. I remember I told you earlier that we can impose a scenario of greenhouse gas changes on a model. And we looked at 2 different types of scenarios that were produced by the global modeling community. Okay, obviously we looked at the historical period and the changes in greenhouse gases over the historical period. And we also looked at our business as usual emission scenario, which I referred to earlier. We also looked at another scenario, which is a much happier scenario. We call this the mitigation scenario. This is the case where the whole world comes together over the next couple decades and transforms its energy production. I didn't intend that to be a joke, actually. And transforms its energy production so as to eliminate carbon emissions. Now, believe it or not, this is a more realistic scenario than the previous mitigation scenario that was adopted by the IPCC, where greenhouse gas emissions just stopped and they looked at what happened to climate after that. This is a more realistic scenario where we transition over the next couple of decades, much like California is doing in conjunction with its greenhouse gas emissions control legislation that is currently being implemented. So in this case, greenhouse gases continue to increase because we can't transform energy production right away, but by the year 2040 or so, they've started to decline. Okay, so these two scenarios, business as usual and mitigation, these are the two outcomes that we're going to be examining in detail. We're going to be looking at 3 different time periods. There's what I'm calling the baseline period. That's the period from 1981 to 2000, the last 2 decades of the 20th century. And then we also have a mid-century scenario. That's the middle 2 decades of the 21st century, so centered right around 2050. And then finally, we'll look at some end-of-century results and see what happens by that point in time. Okay, so everyone with me? Yeah. Okay. Okay, we looked at 4 different aspects of climate. Temperature, of course, the change in snow, the change in wind and the associated impact on fire, and finally, changes in precipitation. There are other dimensions of climate change that we still have to look at, but these are some key aspects that we've already examined and I want to talk about with you this evening. All right, so this is the meat, okay? These are the actual results. Okay, the climate projections for the Los Angeles region. So here's a map just to orient you. We're going to start with looking at some of these warming results. So here we have Southern California, Santa Barbara, Los Angeles, San Diego, Bakersfield. Okay, here is the, and I'm just going to show you some results from August, since August is the warmest month in the seasonal cycle in this region, as it is in many regions in the Northern Hemisphere. Here is the average warming, or sorry, not the warming, the average temperature in August during the baseline period. These are the conditions that we are adapted to, if you will. And you can see over the ocean, it's relatively cool. Over the interior, over the desert, it's warm. At high elevations, it's relatively cool because they're higher, and the coastal zone where we live is kind of in between. All right, now let's look at what happens to the temperature in the mid-century period. This is the period from 2041 to 2060. And by the way, this is the average of all the models. So this is the ensemble mean, or most likely temperature, average temperature in the middle of the century. Okay, you ready? There it is. Okay, so we see a pretty significant warming. Glenn mentioned a number. It's somewhere around 5 degrees Fahrenheit on average. So a pretty different climate. We also see that there's more warming in the interior than there is at the coast. And in general, if you are separated from the coast by a mountain complex, the warming is greater. And the greater that separation is, the more the warming is. That's kind of a rule of thumb. All right, let's look at this then in the context of, in a little bit different context. So now I'm going to show you just some averages over land areas. So I'm going to take these numbers here and just average them over land areas to try to boil this down into something very basic, a question. Okay, yeah, so here we go. I'm going to show you averages now for these numbers. So these are averages over this area. Just the average over this piece of land here. All right, so on the x-axis, here are the numbers that you were looking for, 75 to 90, okay? And here's the baseline period right here, and here's the mid-century period. So here is the average over the land areas. The average is about 77 degrees Fahrenheit if you average over the land. This is during the baseline period. So in the future, that average changes. And this is the business as usual change for the future, about something like 82, 83 degrees Fahrenheit. So pretty significant warming under business as usual. Now, there's also an uncertainty associated with that number because, remember, the global climate models give different outcomes. So this is not just a single number. It's a most likely estimate and an uncertainty. All right, now let's put this in the context of the variability in climate that we're familiar with. We all know there's variability from year to year in climate. So I'm going to put on the left-hand side here some dots that correspond to the average August temperature during every year during the baseline period. So every dot there corresponds to a temperature. For example, during August 1996, that's one dot. Another dot is August 1983. That's just the variation in temperature that we are accustomed to during August. So you can see that the most likely warming, this is the average warming in the future, is the most likely temperature is much higher than any of the summers that we've experienced in the past. So this is the warmest summer right here, and the average warming is actually quite a lot warmer than anything we have experienced. So that red line there is the hottest summer, and you can see that the hottest summer that we have experienced during the baseline period is a couple degrees below the average in the future. So this means that we're starting to move by mid-century into a climate state that is different, noticeably different from the climate that we're adapted to. All right, we also, I said, looked at the mitigation scenario. This is the scenario you'll recall where greenhouse gas emissions are brought under control over the coming decades. And one thing you'll notice about the mitigation scenario is that the most likely warming right here is still greater than the warmest summer that we've experienced over the baseline period. So we still experience significant climate change associated even with the mitigation scenario. So in other words, warming is inevitable. Even in this most optimistic scenario, we still see 70% of the warming that we see in the business as usual scenario. So some climate change is inevitable. And that's one of the main lessons of our study. We also looked at heat extremes, and we looked at the number of very hot days, days that are greater than 95 degrees Fahrenheit. And this is, I'm just going to show you a map of some of these results. So here again is LA, and the pink is the urbanized area. Here are some locations in the region. And this little cylinder here represents the number of very hot days in the baseline climate. So if you look at this over the region, you can see that in Woodland Hills, we have on average something like 30 days above 95 degrees per year. Other locations, for example, very near the coast, have very few days greater than 95 per year because they have this very strong maritime influence close to the coast. All right, let's look at the change in the number of hot days in the future. This is the key, by the way. This is not the actual numbers. This is just giving you the increase, and you can scale that a little bit as you look at these numbers. So here's the change in the number of extremely hot days in the business as usual scenario for mid-century. And you can see that in many areas we have a doubling or even a tripling of the number of very hot days per year. And that this increase, the absolute increase in the number of very hot days, is larger in the interior areas, which is consistent with these areas having experienced more warming. All right, so temperature extremes, obviously a key impact of a changing climate, especially for humans and ecosystems. All right, a lot of people don't think that snow is a big part of LA. But actually, if you think about it, it really is. Obviously, there's the fact that it's pretty to look at in the wintertime behind, if you look at the skyline of Los Angeles. There's the snow there. That's kind of an iconic picture. But we also have recreational use of snow. Lake Arrowhead, Idlewild, of course, are places where we might go skiing. And then we also, perhaps more importantly, we do use a significant fraction of the local snow that falls in the local mountains for water. For fresh water supply. For example, the San Gabriel Valley gets the majority of its water from the San Gabriel Mountains. So this is an important water resource for key parts of the region. And the snow is very important because it acts as a natural reservoir. The reservoirs we've constructed to harness this freshwater resource are only a certain size, and the reason why they are that size is because there's a natural reservoir of snow that we count on to hold the water until we're ready to use it. So this is a really important issue for flood control, the future of snow in this region, flood control and water usage. All right, so here is the average annual snowfall in the baseline period, and you can see, as you would expect, these mountain regions really get a lot of snow. And if you look in the future period, you can see that, and this is mid-century business as usual, you can see that there's a noticeable reduction in the amount of snow that is actually falling in this region. So we do see a pretty significant difference in the amount of snow that's falling by mid-century, consistent with a warming climate. This is just basically because the precipitation that's coming in is falling more likely to fall as rain than it is as snow because the temperatures are warmer. All right, so let's look at a couple locations, look at this from a different perspective. We'll look at Wrightwood, Lake Arrowhead, and Idlewild in the San Gabriel, San Bernardino, and San Jacinto Mountains. These areas in the current, or the baseline climate, get 87 inches, 40 inches, and 87 inches of snow. In the mid-century business as usual scenario, they, in the most likely case, receive about half that amount of snow. And I want to emphasize that we only looked at the change in snowfall. There's also a warming effect on snow melt. Most previous climate studies have estimated that the impact on snowfall in general is about equal to the effect on snow melt. So in other words, if you look at actual snow on the ground, the reduction, half of it is due to the decrease in snowfall, and half of it's due to the change in snow melt. So this change in snow on the ground is going to be even less than these numbers here. So we really are looking at, by mid-century, a pretty significant loss of snow in the high elevations. Now, there's also the mitigation scenario, and this tells a very similar story as the temperature part of the study, as you would expect. In the mitigation scenario, we also see a significant reduction of snow, although it is somewhat less. But it is noticeable, and this just underscores the fact that a significant climate change over the coming decades is inevitable, simply because the climate system is still responding to the changes in greenhouse gases that we've already imposed on it, and it will take us a while to stop emitting greenhouse gases, even if we decided to at this moment. So there's a lot of lags built in that make this inevitable. All right, another really important topic, Santa Ana winds. You'll recall that these Santa Ana winds arise in October. They stem from the cooling of the desert and the fact that this cold, dense air wants to drain out towards the coast, and that generates this windy flow through the passes. And that also corresponds with fire, because the vegetation is dry from the dry season in the summertime. And when those winds come through, they're very dry, they're coming from the desert, and they can whip up big wildfires. And currently, the main source of wildfire, the main climate source of wildfire is the Santa Ana winds. And this is actually a picture of a Santa Ana event that coincided with a bunch of fires. And you can see the smoke coming off the coast towards the ocean. So it turns out that in the current climate, in the baseline climate, we have about 6 Santa Ana days every October. So that's the average number of Santa Anas that occur. What happens to these in the future? This is something that actually really surprised us. The number of Santa Ana days actually goes down in the business as usual scenario by mid-century. And the reason for that is actually pretty simple. It gets a lot warmer over the desert. And you'll recall that these winds arise from the desert cooling off in the fall. And if it warms more in the desert, then that's going to knock the legs out of that drive of those winds to get back towards the coast. They're not going to be as interested in making their way towards the coast, if you will. So that reduces these Santa Ana winds. So we actually have less Santa Ana winds in the future. And the question is, what does that mean for fire? Here is another image of a Santa Ana day in late October 2007. Many of you might remember this. It was a pretty spectacular moment in Southern California. We had fires burning all over the landscape. And you can see the fires, the Santa Ana winds also blowing the smoke offshore towards the ocean. And we had a number of fires really throughout the mountains near San Diego, the San Bernardino, San Gabriel mountains. And the mountains north of Santa Barbara as well. So this is a big, the reduction in Santa Anas could potentially reduce our wildfire risk. But the story is actually more complicated than that, because we also have a different kind of fire in this region. It's not as important as the Santa Ana-driven fires, but it's also climate-driven, and it arises in the summertime. And it basically arises because it's just so hot in this region in the summertime, especially in certain parts of the region. And the prime example of this is the station fire. I don't know if you must remember this. In 2009, there was this, it looked like a nuclear bomb exploded, over the San Gabriel Mountains. There was this giant cloud over the mountains that resulted from this station fire, which burned a huge amount of the landscape. That was not a Santa Ana-driven fire. That was driven just by warm conditions. So we have two competing effects then. In the future, Santa Ana winds go down, so that reduces fire risk. But we also have warmer temperatures, and that increases fire risk potentially. So which one of these wins out, and how does fire change in the future? Now, we undertook a really fun collaboration with some really great fire ecologists at UC Irvine to understand this. They took our data, and they ran a fire model, a model that simulates basically the spread and ignition of fire. And Yufeng Jin and Jim Randerson are their names, by the way. And we have come up with some preliminary results from this fire study that I want to share with you. And I want to emphasize this is preliminary, but I still think it's a pretty good indication of what the final results will be. All right, so here, these are just the number of months. These are just the months of the year, May through December, when basically we have most of our fires. And on the y-axis here is the number of acres burned on average in those particular months. So you can see in the current climate, in our baseline period, the most burned area occurs in October. And that is consistent with the fact that we are in a Santa Ana-driven fire regime right now in our climate. Most of the fires occur during October. All right, so what happens in the future? So here is the business as usual mid-century result. In October, we do indeed see a reduction in the area on average that is burned. And that's because of the reduction in Santa Anas. And November and December, those aren't important fire months. We have a little bit of a change in the future in those months. But mostly during the Santa Ana season, we see a reduction in the area burned because of the reduction in Santa Ana winds. Now, let's look at these other months. These other months are the months where we are susceptible to fire because of hot conditions. So we have a warming climate in the future. How does that heat impact the total area burned? In July, August, September, this is when the station fire occurred, September, we have really large increases in the total area burned as a result of the fact that the temperatures are warmer. The warming, you'll recall, was about 5 degrees Fahrenheit on average in the most likely estimate. That's quite a bit of extra warming. It's quite a bit of extra heat. And that has a big impact on the number of fires. So what we're projecting for the future is that the Santa Ana-driven fire becomes less common. The station-type fire becomes much more common. And that the impact on the total area burned is one where the change in the summer fires wins out. And we have a big increase in the area that is burned. So just to give you some perspective on this, when you add up these numbers over the entire year, you can look at how much total area is burned in the present and in the future. So in the present, we have 76,000 acres burned per year on average. And then in the future, we have 130,000 acres burned per year. So a big increase in the total area burned. And by the way, just so nobody gets confused by this, we're not claiming that these areas are the ones that are going to burn, okay? This is just to give you a sense of the scale, okay? Although, well, no, there's some nice neighborhoods in there. I don't know if I'd want to see those places burn. All right. Precipitation, water resources. We've really only gotten started on this topic, but I want to share with you some interesting results. This is actually an area where there's potentially some good news. This is the current climate, or the baseline climate precipitation, the way it's distributed over the landscape. So we see over the mountains a lot of precipitation. These areas get a lot of rain and snow in the wet season. And they are important, very important for water resources and, of course, also for the ecology of these mountain landscapes that many of us love so much. And in the future, by mid-century, we actually don't see any change in precipitation in this region. And I can go into the details of why that is if you like. But Suffice it to say for now that as far as water input goes, we're not really expecting a great challenge to this region in terms of the total amount of water coming in. However, and this is a really big however, there are many aspects of the climate that shape water resources. Of course, there's how much water is coming in. There's also how much snow is on the ground. And as we've seen, the amount of snow is projected to decrease. So we are losing the natural reservoir that's trapping the precipitation that we're getting. That's very important. We also expect changes in evaporation. Evaporation is a temperature-sensitive process, so we might expect that there would be a loss of water due to an increase in temperature. And then finally, that will all come together and produce an impact on stream flow, and stream flow is really the thing that we care about the most. And then I will also add that much of our water does not come from local sources. It comes from the Sierras and the Colorado. And we need to understand climate change impacts on those regions to really grasp our vulnerability to water resources. And in fact, one of the studies that we're going to be taking on shortly is a similar study to this one, but focused on the Sierras, so that we can understand the changes in water resources in the areas where we get a significant part of our water. So that's actually to come. So we haven't really seen the end of the story on water resources, but so far, so good. All right, so this is where I come out to you as a human being and offer some personal thoughts on what this means for the Los Angeles region. And I think we're on our cheese course in the feast analogy. Let us just talk for a minute about what I think this means for Los Angeles and what this means for us. First lesson, if we choose to respond to a changing climate, adaptation has to be part of our response. We don't have a choice. Adaptation is inevitable. 70% roughly of the change that we see in the business as usual occurs in the mitigation scenario. We have to figure out how to respond to warming temperatures, to less snow, to changes in water resources if we find that they do occur, to effects on ecosystems. I didn't really get into that. Sea level rise, another topic I haven't touched on, that's also coming. And perhaps most important, the change in fire risk. So these are things that we have to plan for no matter what. All right. So I think I can outline some next steps in adaptation. We need to evaluate and strengthen our electricity grid because of the differential warming between areas like the San Fernando Valley and the LA Basin. We need to understand how the electricity grid will be stressed in the future as people crank up their air conditioners. We need to plan for public health impacts. There are populations that are vulnerable to a changing climate. We have to understand how they will be impacted by extremes in heat. Also, there's a sensitivity of air quality to temperature, and we expect changes in air quality due to a warming, and that has to be evaluated and assessed. We also need to find creative ways to cool the city. There's a project, again, that Climate Resolve is spearheading, Hot City Cool Roofs, where we change the reflectivity of the roofs in cities to make them less susceptible to a warming trend. Also the Million Trees Initiative. Obviously, new fire management strategies. I think that's going to be critical. We need to assess our water infrastructure. Are the reservoirs big enough? When we lose that natural reservoir in snow, do we need to expand our current reservoirs to balance that out? And we also need to evaluate and mitigate impacts on wildlife and habitats. These are, I think, some very sensible steps that I think any person looking at this would probably recommend. All right. I want to talk also about this issue of whether adaptation is enough. Of course, I've already underscored that adaptation is inevitable, but is it sufficient? Is it all we have to do? And to address that question, I want to go back to these average August temperatures that I showed you earlier. Remember, we looked at the mid-century most likely warming, the mid-century for the business as usual, mid-century most likely warming for the mitigation scenario, and the range of temperature in the current climate here. You guys all remember this picture? All right, good. All right, and here's the warmest year, and we saw that by mid-century, the average conditions, the most likely conditions are actually quite a lot warmer than the hottest year that we experienced so far. let's look at now another time slice. Let's look at the end of the 21st century. What happens then in these two different scenarios? Well, here is the mitigation scenario. In the mitigation scenario, by the end of the century, we actually are starting to benefit from these mitigation efforts that we've undertaken now. And we are seeing a slight reduction in the average temperature. Let's look at the business as usual scenario by the end of the century. This is the most likely outcome, and this is the uncertainty associated with that. And you can see that even if you're a big climate change skeptic and you believe that the model that gives the least amount of the warming is the true model, this still has a warming that's significantly greater than the hottest summer that we experience now. So this climate here is a different world, a different type of place from the climate that we know now as the climate of Los Angeles. It's a very different environment. And so we really have to think about it in those terms. By the mid-century, we really don't see a lot of benefits from mitigation, but we do see those accruing by the end of the century. So our choices actually do matter. We do have to think about how this is going to impact the future. And I find it helpful to think of this in terms of a timeline and generations. So here we have the present, here's the mid-century, here's the end of the century. You know, who are these people who would be alive in these different time periods? Well, let's imagine that we have some children who are alive right now. Perhaps these are our children, okay? And by mid-century, those two children may have, maybe they got married. They're not brother and sister. They're different children. And they have a child of their own, okay? So, you know, maybe this is our grandchild here, this little person. And then we get to the end of the century, and these little children are now old. They have children of their own who are grown, and then they have their children. So we're talking really about the world of our grandchildren by the time we get to the end of the 21st century. So what's at stake here is our choices and their impact on our grandchildren. That's really what will be the impact of the mitigation measures that we might take. And I think this really captures the very complex and lengthy intergenerational dynamics that this issue raises and the ethical issues it raises. Because climate change was actually set in motion on a large scale by our grandparents, we might call them the greatest generation. They're the ones who really brought this massive emission of carbon to a very large scale and really launched the detectable impacts of increasing greenhouses on climate. They didn't know that they were doing that. They didn't have any idea. So we can't hold them accountable. We didn't do it. We just inherited this world, and we're just trying to keep it going. So we're not really responsible in that sense. The difference is that we know what we are doing, and we know the impacts. And I think that's what really makes someone responsible for something. If they know that something has happened, that makes them responsible for doing something about it. So even though we didn't cause this, and even though we won't benefit directly from our actions, I believe it is incumbent upon us to think carefully about how we should respond. And we have to think about this not just in terms of us, in terms of our children, but in terms of our grandchildren. And we also have to think back in time, too, and think about what our grandparents would have done if they had known. I think about my grandparents. They were Midwestern farm people, really upright people. If they had known this was happening as a result of their actions, I guarantee they would have been in favor of doing something about it. So we have to think about it because of their feelings about me and my brothers and sisters and cousins. So I think those are the terms that we have to think about this. All right, so the road ahead. I believe that we have to continue our leadership in emissions cutting policies. It seems like there's some good news here. California actually has cap and trade legislation in place, and we are actually adopting on our state scale something like the mitigation scenario. That has to succeed. We need to make sure that works so that can be replicated, and that's something that people is seen as a success outside of California. Obviously, we have to transform energy production. We need to get off fossil fuels and onto renewables. We need to implement smarter ways of using energy, get information technology involved in turning off and on electronic appliances. And in Los Angeles, particularly important, we need to complete the great work that we've already started by introducing a low emissions transportation infrastructure in this region. That's really key. Most of our greenhouse gases in our region actually come from transportation. So we need to address that. Oh, and I just wanted to mention, if thinking back again to the challenges that human beings have faced in the past, I think again of my grandparents' generation, they were involved in fighting, they were World War II veterans involved in fighting fascism. These were huge challenges. If you think back to the world of, say, 1940, how daunting would that have been to think about defeating fascism? And they didn't know they were going to do it, but they faced up to the challenge. And I think it's incumbent upon us to do this. And if I look at this list of things to do and compare that to defeating Hitler, this looks like a walk in the park to me. So I don't really think this is all that tough. All right. So obviously we need to understand our responsibility. I think that's part of also the scientific voice in this dialogue. The understanding is what is key to getting us onto a different path, and I think there's an enormous need for further scientific understanding to really get this problem under control. I think we need to take action based on that knowledge. We need to be a little bit more vocal. There's a lot of apathy out there, and a lot of people don't vote, but that needs to change. People need to say something. We need to rethink the way that we live our lives in our cities. Recently, my partner and I bought a new house, and we chose this house based on its proximity to the rapid bus line down Wilshire so that I could get back and forth to work on the rapid bus. And I bought a folding bicycle, and that's how I get back and forth to work now. I go on the bus with my bike, and then I get off the bus and come to UCLA. And often I just bike home. And I actually love it. It's much more enjoyable than being in my car. And I'm actually getting exercise as well. So I think, before I thought, how could I live in LA without a car? And now I think, why would I want to live in LA without a car? So I think we have to rethink our lives and cross that barrier. And this brings up also win-win solutions. That's an example of a thing where I'm actually happier and I'm saving a lot of money because I'm not spending money on a second car. That's a change that makes our lives better and also reduces carbon emissions. So these are the types of areas where I think we really have to focus. All right, so we have future research needs for Los Angeles. I mentioned a few of them. We need to understand, in particular, the water resource question in much more detail. And we are undertaking a study for the Sierras on that. We also need to involve allied fields. This is not just a climate science problem. It's a public health problem. It's a wildfire ecology problem. It's a water resource manager problem. It's an urban planning problem. There are all kinds of areas that are involved in this. And this is why the Institute of the Environment and Sustainability is the perfect organization and why it's so necessary to have this type of thing on campus now, because we need to marshal these academic resources so that we can do research on these issues and understand them. So this is one of the reasons why I'm a really big believer in the IoES. We also need to bring this conversation to other cities. We brought the climate results down to Los Angeles. Now we need to scale up this knowledge. We need to bring this type of technique and this conversation, this scientific advancement, and the discussion about our responsibility and what we need to do in the future. We need to bring this to other global cities so that they can join the conversation and they can also learn about what can be done. So this is another one of my objectives, is to scale this back up in the sense that we reproduce this type of effort in other places. So with that, I thank you very much. I have other, wait. So, I have special thanks also to the funders of this research. This research doesn't happen without money. The Department of Energy, the National Science Foundation, the Los Angeles Mayor's Office. This was facilitated through the Los Angeles Regional Collaborative. Climate Resolve helped a lot with the communications, as I mentioned. Of course, there's my department and the IoES. And then there are some people who have been really instrumental in getting this research funded and implemented and accomplished, and I want to thank those people as well. And I want to mention this website also, which gives you all the information about the project, where you can see these forthcoming studies as they come out, and also some credits. So again, thank you very much.